Welcome everybody, R.1, a new sequence of videos where we start looking at objects that are now rotating. We'll see what that means compared to how we've been looking at things traditionally and introduce the first term for this unit, something known as torque, okay? Well, we're kind of changing our mindset in terms of how we're approaching the motion of objects. Up until now, we've been focusing on objects moving translationally. To be honest, I don't think I've used that term any time before, but when something is moving translationally, that means it's moving from one point in space. Imagine one spot on whatever coordinate system you have, an X, Y, and Z coordinate system, to another location. For example, I have a box, it started right here, and then we pushed it or it moved or whatever, and it ended up here, from one location to another location. But of course, rigid objects, and I say that term on purpose because we're not going to be dealing with like slime or things that can bend and warp easily. It just makes our analysis a little more difficult. But rigid objects, like a wheel, so to speak, okay, it can also move rotationally, meaning the wheel stays in the same location, but it has a different orientation. That's what we mean by rotational motion. So right here, this diagram, I don't know, imagine you have a bike, maybe you flip the bike upside down and you just spin the wheel. Or you take a skateboard and you put it on your table upside down and you flick the wheel. The wheel isn't translating, it's not moving from one location in your kitchen to your living room, but obviously there's some motion involved. It's rotating, its orientation is changing as it's moving, as it's spinning around and around, okay? Well, because we've been talking about translation, a lot of our physics has been physics dealing with what causes, what influences, what changes translation. And the big idea there, at least how we started our sequence of videos, was forces. Forces cause things to translate, or at least they cause a change in translational motion. There's another term, this thing right here, called torque. Torque is the cousin of force. Force causes objects to change their motion translationally. Torque causes things to change their motion rotationally. So that's why we're getting into torque right now, okay? Now, just like you probably have some good intuitive sense about force, you also have some good intuitive sense about torque. Let's look at an object that rotates. And best example, a door. You don't translate a door when you open it. You don't walk up to a doorway, you take the door off, and then you walk it forward or backwards. The door is staying in its physical location, but it's changing its orientation when you rotate it, when you swing it open. So I have this door, the hinge of a door is on one side. I'm kind of labeling it right here. What are some things that affect its change in motion, or what kind of affects whether or not it's easy or difficult to cause this door to swing open? Well, one thing you could probably imagine is force, right? If I walk up to a door and I just try and apply a little tiny baby push, well, the door's not going to open much, if at all. If I really slam my hands into that door, well, you could probably imagine it's more likely to open easier, open more. So force has to do with the rate or the kind of motion of an object rotationally. What else? If you look at these three diagrams right here, imagine I'm applying the same force, that's what this blue arrow is representing, but I'm applying it in different locations. Here I'm applying the force actually on the hinge. That's kind of silly, right? Imagine you go to the door and you push on the door right where the door is connected to the wall. The door is not really going to move at all, or very, very slightly, or it's going to be very difficult. Versus, say, you push in the middle of the door, or you push at the end, the opposite end from where the hinge is located. Well, interesting. The location you apply that force seems to affect how easy it is to open the door, how much you can change that door's motion from being at rest to swinging open. Interesting. That's a little different. Before, the location of the force wasn't really any of significance to us when we were applying Newton's second law. Location does seem to have an effect on how an object rotates versus translates. Well, what else? Okay, let's say we apply that force again, and let's say now it's the same size force, and it's always at the same location. It's always at the far end here. Let's say it's where the doorknob is. By the way, location, that's also why they put doorknobs, of course, at the far side of the door. That location is where it's easy to open the door. But now let's think about the angle we apply the force. Well, if I am pulling on that doorknob kind of along the line of the door, so I'm kind of tugging it along the line, kind of perpendicular maybe, if you will, to the doorknob itself, well, that door doesn't open a whole lot. Obviously, you know, how do you open a door? You push perpendicular to the face of the door. Here, this was kind of parallel or along the face of the door versus maybe some slight angle. Here, I have it perpendicular. Pushing more perpendicular, again, seems to have more an effect. So angle also has to do with the rate things are able to open up. Well, okay. So let's get into some more nitty-gritty physics. I have this door again, and this is a bird's eye view. I know that's kind of maybe a little weird way to think of it, but imagine like you're glued to the ceiling and you're looking straight down on a door. So the hinge is right here and the door is going to swing open, maybe something like that, okay? Well, this torque, how I change the door's motion, it's based on, well, a force that you're going to apply and how far away you apply that force. We're going to call this R. Okay, torque is given this symbol. I'll talk about it in a second. It's based on how far away you apply that force. It's based on the size of that force, and it's based on the angle. Oh, okay, that's what affects the rate of change for rotating things. Okay, so here are the official notes for what's called torque. Torque is this thing that affects the change in an object's rotation. Lowercase Greek letter tau, that's the symbol we use for torque. It's kind of like a scripty, fancy-looking T. That's what I've drawn right here. Torque is based on R, how far away a force is applied. And also, remember, it was based on location, force, and angle. It's also based on the perpendicular force. Now, this arrow right here is already perpendicular. So you might just see this written as R times F, like this. Okay? But if it's not, you should be using a component of the force. Yes, we're still dealing with components that are perpendicular. It's the radius and the force that are perpendicular with one another. I had to move my head up a little bit. My apologies. R is measured, what I've drawn right here, or of course it could be uppercase R or lowercase r. It's measured along the object, meaning here's my door. We have a nice rigid object. If I go along the door to where that force is applied, that's how I recommend you imagine thinking, okay, that's how I measure the radius, how far away this force is acting. Okay? It's this measurement from the hinge, from this sometimes called pivot or axis of rotation, to where that force is applied, along that rigid object. Okay? The units for torque, well, it better match the units of my equation. It's R multiplied by F. That's meters times newtons. Or, you know, they're just multiplied, so the order doesn't matter. Conventionally, it's written like this. The units for torque, those are Newton meters. Okay? Now, again, here was an example where the force was already perpendicular. When I say perpendicular, I mean, you know, this is my R going along the doorway like this, and this is my angle theta. And this is already 90 degrees, okay? So no difficulties here. But now I'm going to switch on over to a slightly more difficult scenario, moving my head back down. So again, let's say that the distance along this door to where the force is applied, I'll call this R, okay? The torque is equal to R times F. Technically, it's the force that's perpendicular. If this is my force right here, this force is not perpendicular. So what do I have to do? I gotta break the force into components. So I'm gonna draw the force like this. There's my F. If this is my angle right here, this is theta, well then what I'm drawing, this right here is Fy, or, because relative to this radius along the doorway, that is the perpendicular piece, well that's adjacent to my angle. Well, okay, let's see. Cosine is adjacent over hypotenuse. So F perpendicular, that would be F times the cosine of theta. So what is my torque equation equal to in this scenario? It's R times F cosine of theta. Now, if you're thinking, well, wait a minute, Thrasher, what if, in fact, you drew your force vector or the angle that was given was actually like this? What if this was the angle given? And that's possible. To be honest, in textbooks, you often see it written like this, as if this cosine theta is the definition. But that's actually a little dangerous. It's not that it's always F cosine theta, or even it's always F sine theta. It's that you're using the force and the radius that are perpendicular to one another. So let's say in the problem it actually has what I have in green here, and they gave you this angle, so this angle right here. Well, again, you always want to use the perpendicular component. That would still be this piece. I'm not saying it's changing our triangle, but if we're given this angle, that's the opposite side. So here, F perpendicular is F times the sine of theta. Now, admittedly, this theta here would not be the same as this theta. They would what? They'd be complementary. Okay, but depending on what angle you're given, well, you might be using sine or cosine. What is most important? The equation for torque is R times the force that's perpendicular, or in this scenario with my green angle, that would be R times F times the sine of theta. So you might actually kind of be deriving slightly these equations as you go. One thing, I'm going to jump back right here. Some college textbooks, and if you go online, you might see people breaking down the radius into components. You can. I'm not actually going to spend time showing that in this video because all semester or all year, if you've been following along my videos, we've always been breaking forces into components, and that's what we were used to. So I'm always going to stick with this, the idea of breaking the force into components, depending on if you search for things online or maybe you've done some torque learnings in the past. Maybe you're okay and you're familiar with breaking down R. You could do that on any one of my tests or quizzes, and I'll give you full points, but it's a little rare, and I don't think it's quite as intuitive, okay? But that's torque. Torque is what affects the motion of something in a rotational sense. It's based on the location of an applied force, the size of that force, as well as that angle. Okay, there's one more thing I want to spend a little bit of time on, and that's a pulley. We've actually talked about pulleys in the past before. Pulleys are a way to redirect a string or a way to redirect a force. Now, here's an actual kind of real-life pulley, if you like, but here's a classic kind of diagram. Let's say I have this pulley, so it's a little tough to see, but imagine this is a string, and the string is, kind of looping around over here. We're just going to imagine one force acting on this pulley for right now. We'll see multiple forces in the future. But this is, again, something that's going to be rotating, right? Like that bicycle wheel, like that skateboard wheel. It's going to be spinning around and around. It's not translating, it's rotating. Before, we kind of ignored the pulley itself, but now we're really going to focus on the actual motion of this pulley, okay? Now, of course, there's some pivot point, there's some hinge. That's, in this case, the actual center of the pulley, right? Because it's circling around that center. So my R would be this. And there's this downward force. So my R is like this. That would be 2 centimeters, right? The diameter is 4 centimeters in this picture here. And the force, this 30 newtons, is like this. F equals 30. Notice, the force is almost like automatically perpendicular to my radius. So unless something really weird is going on, these pulleys are actually kind of easy. The torque is still based on R times the perpendicular component, but you're pulling straight down tangent to this circle. Even if you were pulling, say, the string this way, well, that's still perpendicular to the radius. So that's just going to be R times F. If you were plugging in numbers here, I don't know, 2 centimeters. If I put that into meters, that would be 0.02 meters times the force of 30 newtons. And then bam, you could calculate something and get the total amount of force in Newton times meters. Okay? We'll look at what happens when there's multiple torques, apply it to energy and momentum later on. But this is the basic idea. Now we're looking at things rotating, and there's a new fundamental cousin of force, that's torque. Okay? Thanks a lot for watching. I'm out.